introduction, even though I'm remote. So probably can't see me more than a small box, but I'm hopefully that's okay. So it gives me great pleasure to introduce Mr. Naveen Arunachalam. Naveen earned his bachelor's in chemical engineering from Caltech in spring 2018. It's been a real adventure to see how Naveen's interests developed over the years. Naveen's been integral to our group's web front ends for many of the research front efforts in our group, from those about MOFs to transitional complexes. He's also simultaneously revitalized the group's lunch culture and contributed strongly to the fabric of the group, always finding a way to stretch the group meeting food budget to the last cent. One of the most singular things about Naveen is how he always takes a lighthearted approach to research. He's given group meetings themed after everything ranging from the Tiger King series to Spotify or any number of pop culture references I usually have to look up. I'm excited to see Naveen branch out as a consultant in the area of AI and computational chemistry as his next step. And without further ado, Naveen, the floor is yours.
Thank you for the kind introduction, Heather. So today I'm going to be talking to you guys about my work in the autonomous first principle design of transitional complexes. So my hope is that this talk will be both informative and entertaining as you learn what I've been up to the past 5 years. So ever since the beginning of time, no, I'm not going to do that to you. Ever since the beginning of time, humans have wondered how we could accelerate the design of new and useful compounds. We want to make new things that can help improve our health and our well-being. However, when it comes to discovering new compounds, this process is tedious. Planning and synthesis in the lab takes a long time. So when it comes to screening new compounds for use in everyday life, it takes weeks to months to screen each one in a lab setting. So one potential solution that we can use is using computation to screen compounds that can be assessed in the lab. So on this screen, I show on the left the fact that you might have a design space of millions of potential compounds that you want to study. For example, one possible type of compound is drug candidates. And next, you might want to filter the most promising candidates so that you just have a few leads to study in an experimental setting. So this is quite abstract so far. So I'll show you an example of a success story of using computation to screen candidates. So in 2019, Jabranikov et al. Used machine learning and computational chemistry to screen through a large pool of fibrosis cure candidates. So on the left, you see a picture of some potential drug-like molecules, and they screened through this huge chemical space in just 21 days on a computer. Then it took about a month more to test the top 4 compounds in mice, and one showed promise as a cure. And what these guys did was basically finding a needle in a haystack, and that's going to be the theme of this talk. How do we find the needle in a haystack for some kind of chemical question we're trying to answer? So a question we might have is how we can apply this to other fields. I showed you how we can apply it to drug candidates, but how can we apply it to energy storage, for example? If we want to make grid-scale batteries to power a green world with solar power and that energy being stored at night when the sun isn't available. How might we apply it to catalysis? The catalytic converter in your car actually uses catalysis to filter out the emissions from your car and result in a clean output. And the next question we have is how we can use it for separations. For example, natural gas purification is used to make natural gas burn more cleanly by removing compounds that would result in toxicity when burned. Now, if we look at the secret sauce behind all 3 of these categories, it turns out to be transition metal chemistry. So if we look at some key molecules in energy storage that you could find in redox flow battery candidates, if you look closely, you'll find that the metal center in these compounds include iron and cobalt. You might recognize these as metal names. If you look inside your catalytic converter, the secret sauce is a set of metals, platinum, palladium, and rhodium, which are used to convert noxious fumes to less noxious fumes. And lastly, in separations, you might look into metal organic frameworks, which are used to separate gases from each other. And if you look at the structural units of metal organic frameworks, you'll find these zinc atoms. And zinc, again, is a transition metal. So what's going on here is that in these fields, it turns out that the best-in-class compounds happen to be inorganic ones. So when we look at these three areas, we might be interested in optimizing an inorganic chemistry. Now, the biggest challenge to discovery in inorganic chemistry is that there's too many compounds to screen and too little time. So here I show an example of a transition metal complex, which is sort of a model system to show the interaction between a metal and the atoms surrounding it. So on the left, I show a ball and stick model of a transition metal complex. In the center, we have a metal atom, and it's surrounded by 6 ammonia ligands. And the cartoon representation of it is on the right, where I have N for the metal and 1, 2, 3, 4, 5, and 6 to represent the ligands. So to try and emphasize how large this design space is, I'll show you a few transition metal complexes that are valid. So let's take this cartoon representation of the metal surrounded by 6 different ligands, or possibly the same ligand. And on the bottom left, I show an example of a metal surrounded by 6 water molecules. So that's one possible compound that we can make. We might vary things up by changing the ligands around the metal center. For example, in this one to the right, I've replaced some waters with ammonias. And over here, I've replaced some ligands with furans. And over here, I've replaced some ligands with methyl isocyanide. And as you can see, we're starting to span a range of length scales. We're starting to span a range of ligands. And if we're feeling ambitious enough, we can make this huge behemoth that's metal isocyanide ligands surrounding a metal atom. So as you can see, there's a huge range of levers that we can pull in designing these transition metal complexes. In fact, a study estimated that there's about 10 to the 60 organic molecules that can possibly be designed by human scientists. And many of these ligands and many of these molecules can be used as ligands in the scaffold. So it turns out that this 10 to the 60 choices of ligand is about as large as the number of stars in the galaxy. So the possible number of transition metal complexes is so large that it would be impossible to exhaustively screen all of them, even with computers. So then the question we might have is, how much computation can we fit into computers? So when it comes to computational screening, one way we might go about it is through physical simulations of compounds. So this is where we might literally simulate the electron cloud around every single atom in a system and see what happens to it over time. We simulate an entire reaction. Or we might use ball and spring models to make these slightly faster. And the good thing about these physical simulations of compounds is because they have some correspondence to the real world. They're working based off physical principles. However, because they're working off physical principles that you need to propagate over time, these methods can be time consuming. On the other end of the spectrum, we have inferences from data sets. And specifically, I'm referring to machine learning. So one advantage of machine learning compared to physical simulations of compounds is that machine learning can be lightning fast. If you have a trained model, you can give molecules an input and get a property prediction as an output more or less instantaneously to our eyes. But the problem is that the accuracy of these models depends on your training data. If you have not so good training data, your output will be not so good. Unlike the case of physical simulations, where you're working with a model that's somewhat tied to reality, and even if you're exploring very new chemistry that's not like any data you've seen before, you might be able to get reasonable outputs from it. So going back to the original question, which is how many molecules can we screen using these methods? First, we'll look at physical simulations of compounds, the first method I alluded to. So in order to do this, we might use density functional theory. Density functional theory is a de facto standard for screening transition metal complexes, or TMCs. And the way this process works is that we take a physical structure or a guess of a physical structure. For example, if we want to study a metal atom surrounded by these ligands, we will feed this information to the computer in the form of the XYZ coordinates of each atom. Then a program running density functional theory calculations will take seconds to minutes to assess the electronic structure of the molecule. So that means the shape of the electron cloud surrounding the atoms of the molecule. And from this electronic structure, we can compute several properties, such as the ground state energy, the spin splitting energy, the ionization potential, and redox potential. So the main idea here is that when we run a physical simulation of a compound, we can get properties out of it on the order of seconds to minutes. Now, there's one problem, which is that if we don't know the precise physical structure of the molecule we're trying to study, we'll get junk outputs. So what do we do if we don't know the precise physical structure? We will use an initial guess structure and use DFT to assess the energy of that structure and move the atoms around until we reach an energy minimum. So because each assessment of energy takes seconds to minutes, the total optimization of the structure will take minutes to hours. And here I've included an actual DFT optimization for my calculations, where in each frame of this animation, the computer is taking seconds to minutes to calculate how to perturb the atoms to minimize the energy of the structure. So the conclusion from this is that because it takes minutes to hours per calculation, we can only screen hundreds of thousands of compounds per year, which pales in comparison to the 10 to the 60 molecules that comprise the transition metal chemical space. So a question we might ask is if we can do better, if we can screen more molecules in the same amount of time. And that's where inferences from data sets or machine learning comes in. So machine learning models take in a training data set, such as a large table of molecules and their properties. And these data sets can be computed using DFT simulations, or they can be discovered in lab. You can run hundreds of reactions and tabulate them into such a data set. So in the case of machine learning, again, you start with an input structure, probably a guess structure based on what atoms you believe should be in the molecule. Next, you feed it into an ML model. I'm leaving it as a black box for now, but I'll explain this part. And the ML model will create your property prediction, just like the DFT process. So to kind of uncover this black box of what's going on in the ML model, I'll show a simple example here of a neural network. So the inputs to this machine learning model in this example is a vector of length 3, and the output is a vector of length 1. So what a machine learning model does is that it takes a data set of vectors, mapped to vectors, and it learns relationship between those two sets. So for example, the inputs to such a neural network could be a molecule, and the output could be a property. Now I know the question you have is, wait, a molecule is not a vector, so I'll answer that too. So in our group, we use the molecular fingerprints that we call RAGs, or revised autocorrelations, to quickly turn transition metal complexes into vectors so that we can feed them into machine learning models. So on the left, I show an example of a transition metal complex. And from this complex, we only need the connectivity. We only need the list of which atoms are connected to which atoms. We don't need to solve the precise structure like we did in DFT, which could take minutes to hours. And instead, we just go based off our guess structure. For each atom in the molecule, we take the atomic properties, such as the nuclear charge, electronegativity, topology, and covalent radius. These are numerical quantities. And we perform autocorrelations. We perform products and differences on the molecular graph of these atomic properties to result in a fingerprint vector, which I show on the right. And this fingerprint vector can be generated in just a few milliseconds to seconds. So going back to our flow chart for data-driven discovery, we start out with a physical structure, feed it into a machine learning model, and get a property prediction out of it. But now we know a bit more. We know that it takes milliseconds to seconds to convert a molecule to a vector. Then we know that the vector is fed into a machine learning model, and the machine learning model can produce a property prediction in milliseconds or less. So what we learn here is that because it takes milliseconds to seconds for calculation, we can screen billions to trillions of compounds per year, which is way higher than we were before with just DFT alone. Now, as I mentioned earlier, machine learning model quality depends on your training data set quality. And I'd like to emphasize that in inorganic chemistry, we've tended to lack the training data that was available in organic chemistry. Because organic chemistry is related to drug discovery and so on and so forth. Lots of large data sets of molecules have been curated. And on the left, I show the number of organic chemical structures and their properties that have been computed in databases in 2019. And that number is 3 million. On the other hand, in 2019, for inorganic chemistry, the largest database of structures and their properties for transition metal complexes was only about 1,250. So as we can see, there's a lot of work that we can be doing to get the data sets up to par. So we need more data. So in order to get more data, our approach is to accelerate the design of new materials first and foremost. But the way we do that is by starting with DFT calculations to get a database of structures and their properties, feed that information into machine learning models, which can be used to suggest candidates for lab experiments. And this is how we just find the needle in the haystack. So the first thing that we might want to do is go from a massive design space, 10 to the 60 transition metal complexes, and narrow it down to just a few thousand or so transition metal complexes that we want to run DFT calculations on. So these are the calculations that can take minutes to hours each. And by doing that, we can create data sets that we can train our machine learning models with. So work that I've done relevant to this include DFT calculations on diverse ligand fields. In this image here, you see some examples of ligand fields that can exist around a metal. And in this work, we exhaustively go through some of these ligand fields. The second part of this is doing DFT calculations on diverse metals. So here I show some examples of metals from the periodic table. Starting out, we just had DFT simulations for chromium, manganese, iron, cobalt compounds. And during the course of my PhD, I worked on generating data related to the next period of the periodic table. And one of the takeaways here is that our data curation choices, such as the diversity of our data set, can go a long way for improving our machine learning model performance. Step 2 of what we might want to do is to take these data sets of thousands of transition metal complexes and their properties and train machine learning models that can quickly screen through billions of transition metal complexes. And the reason why I want to do this is because by improving our data sets, we improve our machine learning models, which can allow us to find better candidates for lab experiments. So for the second step of training machine learning models to screen larger spaces, I worked a bit on using diverse training data to improve machine learning model performance in new domains. So by this, I mean using our existing data set of compounds on this period of the periodic table and performing calculations on the next row of the periodic table to inform discovery in that area of chemistry. And on the right, I show how we've used machine learning models on experimental data. So we go through databases of experiments cataloged in the Cambridge Structural Database to predict the synthesizability of new transition metal complexes. And by pushing into new domains, using machine learning models trained on new data sets, we can expand our chemical horizon and look at new chemistry. And the third thing that we'd want to do once we develop these machine learning models is to provide insights into the machine learning models predictions so that we can provide candidates for lab experiments that people can understand the reasoning behind why those candidates were proposed. So a goal here in this step is that our machine learning models should be inspectable and open to review by experts. So for this third step, some of the work I've done is developing web interfaces for our machine learning based property prediction models. And using these web interfaces, we allow experts to participate in interactive design using machine learning models, and we can collect feedback from these experts. And the three websites that I show here are MolSimplify Lite, MOF Simplify, and Ligandify. So as for the structure of this talk, I'm first going to go over my work related to data set augmentation, so generating new data in new domains of chemical space, and our work on machine learning model training on these new regions of chemical space. Then the second part of my talk, I'm going to talk about the web interfaces that we developed to improve the accessibility of our machine learning models. So to start with this section, I want to reiterate that design space is vast. So here on the left, I show an example of a transition metal complex and the scaffold that's a cartoon version of this transition metal complex. And on the right, I show some of the choices that we can have for the metal. And it's a finite number, we can count it on our hands. But next, when it comes to the ligands, again, we have about 10 to the 60 choices. There's a huge diversity of ligands that we can choose to compose these transition metal complexes. And in fact, some of our work used enumeration mathematics to show that if we have 12 choices of ligands, we have about 82,000 possibilities of transition metal complex. If we have 5,000 choices of ligand, things get really hairy with 6 times 10 to the 21 possibilities. And going through all these possibilities would take 190 trillion years to screen through, even with machine learning. So a question that we might have is how we can make screening more tractable. So in the previous slide, I showed a ton of scaffolds with different arrangements of ligands around a metal. And the question is whether we can sort of infer the properties of these for free using a smaller number of calculations. So what I mean by this is on the left, I show an example of two complexes, one with all A surrounding the metal and one with all B surrounding the metal. And we might wonder if a compound with 3B surrounding the metal and 3A surrounding the metal is just an average of the properties of these two other complexes. And when I'm talking about properties, I want to show you an example of a property that we might be interested in studying, which is spin state ordering. So here I show a transition metal complex in octahedral geometry. And around the metal, there's a set of 5 canonical orbitals. And the main thing to know about these orbitals is that there's a dz squared orbital that's vertical, it's the one on the very right, which breaks the symmetry in the molecule, which means that whether two molecules are trans to each other matters. So when I'm referring to trans, I mean this top atom and this bottom atom. These two atoms are considered trans to each other. So there's a unique significance to the fact that two atoms are trans to each other, which has a large implication on the properties of these mixed compounds that I referred to earlier. So let's look at two examples of transition metal complexes and what happens to the electron cloud around them when we use different ligands. So on the left, I'm showing an example where we substitute A with cyanide. And on the right, I show an example where we substitute A with water. So let's see what happens to the orbital energies. So on the left, I show the energy gap between the EG and T2G orbitals. Basically, these 5 canonical orbitals can be reformed into these EG and T2G orbitals. And the gap between them is determined by the ligands surrounding the metal. So when we use cyanide, which is a strong field ligand because it induces a large separation between these orbitals, we get a low spin complex. We call it low spin because the way that the electrons populate these orbitals is by pairing up in the bottom set of orbitals. So there's no unpaired electrons. So because of this, the net number of unpaired electrons is 0, which makes it low spin. On the right, we have a weak field ligand, which is water. And because of this, the splitting between the EG and T2G orbitals is smaller, so electrons are able to populate the higher energy orbital. And because of this, some electrons remain unpaired. In this case, 4 remain unpaired, and this complex would be considered a high spin complex. So some properties that might come out of this orbital diagram would be EHS and ELS, which are the high spin ground state energy and the low spin ground state energy. So for each of these complexes, for the cyanide complex and the H2O complex, we can force them to be in a high spin configuration or a low spin configuration and measure the energy of those configurations using density functional theory. So on the left, we will have 2 energies that we get out of it, the energy of the high spin configuration, energy of the low spin configuration. And on the right, with water, we also get these 2 energies. If we subtract one of these from the other, we get the spin splitting energy, which is the energy of the high spin state minus the energy of the low spin state. So each of these molecules, the cyanide one and the H2O one, have a spin splitting energy, which can be measured using DFT. So as I mentioned earlier, we might be suspicious that we can infer the properties of these mixed compounds based on the properties of these homoleptic ones with the same ligands surrounding the metal. For example, we might imagine that because there's 3 A's in here and there's 6 A's in here and 6 B's in here, we just take the average of the properties, such as the spin splitting energy of these compounds, and average them, and then we can approximate the properties of these mixed ones. But the problem is, if we take that approach, we'll end up saying that the FAC isomer and the MER isomer, stands for the facial meridional isomer, we'll end up assigning them the same energy because both of them have 3 A's and 3 B's. But in reality, these 2 compounds have different spin splitting energies. So what we'll have to do is figure out whether isomer differences are worth worrying about, and if so, figure out how to predict them. So we start with a data set of homoleptic complexes, which contain the same ligands surrounding the metal. And we also use binary complexes, which contain 2 different ligands surrounding the metal, in this case, L1 and L2. So when we screen through a small space of these compounds, for example, we looked at mixtures of acetonitrile and water for A and B, acetonitrile and carbon monoxide for A and B, and carbon monoxide and H2O for A and B. We plotted the spin splitting energy that we calculated using DFT against the predicted spin splitting energy on the y-axis using this averaging rule. And it turns out that this averaging rule actually performs quite well. If we look at the mean absolute error of this formula, it ends up being 3.4 kilocalories per mole, which is within chemical accuracy. Now, you might notice that there's a lot of points that are horizontal to each other on this chart, and this corresponds to the isomers where we predict the same value, but they actually have different values. So a question we might have is whether we can make better interpolations. Because the FAC isomer and the MER isomer have different properties, we might be interested in breaking the symmetry by using 2 other isomers with different energies to calculate the energies of FAC and MER. So in this case, we're going to look at cis and trans. So when two atoms or 2 molecules are cis to each other, it just means that they're adjacent. So this B and this B are adjacent, this B and this A are adjacent, and they would be considered cis to each other. So this isomer is considered cis because it has two A's adjacent to each other, and this one's considered cis because it has two B's adjacent to each other. And because the FAC isomer has more cis interactions than the MER isomer, we might use cis isomers instead of trans isomers for this mixing rule. On the other hand, for the MER isomer, we can use trans isomers because the MER isomer has fewer cis interactions. So now that we've broken the symmetry, if we run an averaging formula using the formulas on the previous slide, we find that the error of prediction here is 1.6 kilocalories per mole. So we've improved. So the main takeaway here is that we can estimate the difference between isomers using mathematical rules on other isomers. And the next question we might have is, what if we increase the complexity? What if we look at ternary complexes, which with up to 3 different ligands? So again, we might take a more naive approach, which is to ask whether a complex containing 2 A's, 2 B's, and 2 C's can have a property estimate based on this complex with 6 A's, this one with 6 B's, and this one with 6 C's, and divide that by 3, because 6 divided by 3 is 2, and you have 2 of each. And if we actually implement this, we find that this process has a mean absolute error on our set of ternary complexes of 3.8 kilocalories per mole, which is small. This is good. Now, one issue is that this averaging system is blind to differences in isomers. For example, I showed 2 isomers that look very similar at first, but are actually quite different. So because of the DZ squared orbital breaking the symmetry that I mentioned earlier, the fact that the 2 A's are trans to each other on the right and they're cis to each other on the left means that they will end up having different properties. They'll have different electronic structures. So one potential solution that we can implement is to again include trans and cis DFT calculations to break the symmetry and include them in our interpolation formulas. For example, this compound with many cis interactions can be approximated by averaging all binary cis complex energies. And this one on the right can be formed by averaging some cis and trans complex energies together. And as you can see, we've improved with a mean absolute error of 2.4 kilocalories per mole. So to summarize, to calculate the properties of 29 ternary complexes, if we're looking at a set of 3 ligands, we can take the naive approach of doing 3 DFT calculations on the uniform versions of these complexes, one with all ligand A, one with all ligand B, and one with all ligand C. And this approach gives a mean absolute error of 3.8 kilocalories per mole. And the approach with including cis and trans calculations takes a bit more in terms of DFT calculations, but results in a 2.4 kilocalories per mole error, which is better. And the idea here is that we can use either approach in a screening setting, depending on our computational budget and our accuracy needs. So when it comes to screening, we might be interested in screening real world complexes. So what we did is that we combed through the CSD and found 56 ligands that are used in experiments. The CSD stands for the Cambridge Structural Database, which is a depository for experimental structures. We performed 56 initial DFT calculations and plotted the 2 properties of HOMO level and the spin splitting energy against each other. And our design target is to find spin crossover candidates with good oxidative stability. So what I mean by this is compounds with the spin splitting energy between -4 and 4, so that their spin splitting energy is close to 0, and have deep HOMO levels, in this case, in this region beyond the one that we find in the CSD. So when we run homoleptic interpolations on only 56 DFT calculations, we end up generating tons of property predictions. We generate 800,000 of them. And here I've plotted a heat map of the interpolations between these orange points, which are the DFT calculations. And we find that the DFT on a validation set using this method is mean absolute error of 4 kilocalories per mole. And what we've done here is that we saved 99.99% of our DFT calculations by only doing 56 out of 800,000. So the summary here is that we can simplify our design space exploration by only studying a few key transition metal complexes. So next, I'll be discussing another aspect of design space. So on top here, I show an example transition metal complex, and we can look at the ligand field surrounding the metal. We can look at the ligand field symmetry, but we can also look at the metal in the transition metal complex. So in our group, we do a lot of calculations on complexes containing 3D metals, which exist on this third row periodic table. But there's a lot we don't know about 4D metals. So the question is whether we can use our data sets for 3D transition metal complexes and transfer that information to 4D transition metals. So in order to investigate this, we performed DFT calculations on a 3D and 4D data set with a diverse set of metals from both rows of the periodic table, diverse set of ligands, and diverse set of ligand fields. And one interesting result from this work is that we found that the interpolation rules that I mentioned in the previous part still hold for 4D complexes. So on the bottom, I show that iron complexes, as you increase the number of A ligands to B ligands from 0 to 6, you have a somewhat linear relationship between the spin splitting energy and the number of ligand B. The same holds for ruthenium, which implies that we can continue to save calculations for 4D complexes as well. Additionally, we find that 3D properties highly correlate with 4D properties. On the right, I show an example of the ligand dissociation energy for 3D and 4D complexes plotted against each other. And we can see that there's a very nice linear fit between them with an R-square of 0.91. And if we train a linear model on this, we get an error of 9.69 kilocalories per mole, which is not exactly within chemical accuracy, but it's still fairly good. For the ligand dissociation energy, which I plotted here, this value is 4.88 kilocalories per mole. So the main idea here is that using linear models like the one on the right, we can save ourselves many DFT calculations by inferring 4D properties from 3D data. So a question we might have is whether we can do better than this linear model. And one way you can do this is through machine learning. And there's two tricks that we can use to improve our machine learning models. So the first thing we can do is include a small amount of 4D DFT calculations, about 2%. Into our data sets, so our machine learning model can learn correlations between 3D and 4D data. For the second trick, we can look back to our previous slide about our fingerprint vectors, where we take atomic properties and convert them to vectors. And add an additional atomic property, which is the group number. So by adding the group number, we associate metals that are in the same column of the periodic table with each other, which makes it easier for a machine learning model to pick up on the relationship between the two. So it turns out that if we take the linear regression approach mentioned earlier, for spin splitting, we get an error of 9.69 kilocalories per mole. Also, linear regression requires a balanced data set of 3D and 4D complexes, whereas with machine learning, we only need 2% of the training data to be 4D complexes. And this results in a mean absolute error of 9.11 kilocalories per mole, which is an improvement. So the main takeaway here is that with machine learning, we can obtain similar performance to linear models using much less training data. So to conclude this part, we did an investigation of diverse metals and ligand fields, which has improved our ability to screen new chemistry. And having more data means that we have better machine learning models, which improves our ability to explore new types of compounds. And the overarching result of this is that in 2019, our group had a database of 1,250 structures and their properties. And due to our group's efforts, and inclusive of the efforts mentioned before, we now have a database of over 150K structures and properties. And yes, I did scale the circles appropriately based on the numbers. So for part two, I'm going to talk about interactive design. This part's going to be a little more on the fun side about using web interfaces to interact with our machine learning models. And there's also live demos though with QR codes. So if you have your phone with you, you could try them out. So let's go back to our original slide at the beginning. Our main question was how we can accelerate the design of new and useful compounds. But over here, we're making a lot of machine learning models, and we're doing a lot of computation. And the idea is to eventually propose some candidates that will be screened in an experimental setting to validate their usefulness. And this reminds us that the machine learning models that we develop have end users. And these end users are people in experimental labs who want to find lead candidates to study. So our group has produced data and machine learning models to predict properties of transition metal complexes and for metal organic frameworks, which are particular materials that contain transition metals. However, these models can be opaque to chemists working in the lab because they exist on the computer, you have to go through installation, you have to deal with vectorization and so on and so forth. So the question is how we can let experts interact with these models to design new molecules. And there's two ways we can go about this. We can make an end-to-end ML pipeline. We can basically ask someone in a lab to request a molecule with characteristics X, Y, and Z, and then voila, they get a molecule. Or we can offer chemists a way to participate in the design. So by interactively working with this black box ML model, by viewing some of its internals, this increases the transparency of the process and allows the user to use their own expertise to collaborate with the model to find better leads. So when it comes to interacting with machine learning models, especially on the lab side, there's a few issues that people tend to face. So installation can be an issue, software updates can break whatever user interface you're using, and installation might not even work on some machines, whether you're working on Windows or Linux or so on. And in the group, we've seen this happen a few times with the most simplified Python interface, which is why we're interested in making it more accessible. So the solution that we're using right now is to use the web browser as a user interface. And the question is, why use the web browser as user interface? So you might be familiar with the icons shown here. It's Slack, Discord, VS Code, and Spotify are old friends. And it turns out that all these use web browsers in the background. Actually, you can do some tricks to like open up inspect elements and edit the HTML in these apps. So they're really using a web browser in the background. And the question is why they're developed as web apps. And the reason is because there's no installation required beyond just having your browser. So these apps just use your existing browser tools in the backend. And websites also let end users in chemistry try out our machine learning models without having to install anything. And web browsers work on all operating systems, whether you use Windows or Linux or Mac. Another advantage of using the web as a user interface is that you can write your code once and run it anywhere because browsers are available almost ubiquitously. And if you target the browser for an app, that app can be deployed almost anywhere. So I'm going to go over quickly 3 examples of using the web browser's user interface, which are MolSimplify Lite, MolSimplify, and Legendify. So for MolSimplify Lite, what we wanted to do was take the original user interface, which was launched from Python, and the user interface can be used to predict bond lengths and electronic properties of molecules using machine learning. And I'm going to talk about how we convert this to the new UI, which is a website. So at the QR code on the top right, you can access molsimplify.mit.edu. And this run-through shows that you can specify the components of a transition metal complex. Click Generate to view the complex. Then you can use the Predict button to predict a spin-splitting energy using our machine learning models. You can plot how that spin-splitting energy compares to the training data of those, the training data used for the machine learning model. And you can view a principal component analysis, which shows where roughly your compound is located relative to our training data. if you compress it into a 2D space. So the features I want to point out for MulSimplify Lite are interpretability aids, which include a demonstration of where your compound falls relative to training data, and this PCA plot, which shows where your data is localized relative to the training data. So if you see your complex embedded in the training data, that means that the machine learning model knows a lot about complexes like yours. If it's far away from the training data, then you know to trust the machine learning model a bit less because your data doesn't correspond to the training data. So the key takeaway is that visualization can help users understand machine learning models and their training data. And here I'm showing a case where we add an upgrade to the website where we add an extra machine learning model that we developed as an extra button on the site. So in 2022, our group developed an additional machine learning model to recommend simulation parameters for DFT. And when you uploaded this feature, it only had to be installed on our host computer, the computer that's hosting the website. And as a result, users were able to immediately try out the results of our new publication without having to install any software. So this shows the power of web interfaces to help users interact with machine learning models. Next, I want to talk about MulSimplify, which we use to accelerate the design of MOFs. So MOFs are metal organic frameworks. They're reticular materials consisting of these secondary building units, which contain metal atoms and linkers. And these two components will self-assemble into this grid-like structure in 3D. And with MOFs, just like transitional complexes, they're both inorganic compounds. They have a vast design space that can be screened with machine learning. Both are used for MOFs are used for gas separations, so they're useful in that way. And the question we have is if we can also help users interact with our machine learning models for MOFs, as well as those for transition metal complexes. So when it comes to the design of MOFs, there's a few considerations we have. The first is stability during synthesis. So we might look at the solvent removal stability because you have to remove the solvents during the synthesis of MOFs, and if they fall apart during this process, then you just don't have a working MOF. Also, we'd be interested in their stability during operation. So they're operating at high temperatures. We don't want them to thermally degrade. So we want to look at their thermal stability. So our group has data and machine learning models for these properties. And the question is if we can let users provide feedback in these models. So the solution to this was developed by my colleague John Marco in MulSimplify at mulsimplify.mit.edu. You can scan the QR code. This is a walkthrough of breaking down a MOF and visualizing it. So as you can see, you can get quite a lot of data about your MOF from this website and do some predictions on it. So what I want to draw your attention to is how we obtain feedback from users. So we implemented a feedback front end, which is a set of forms that allow users to comment on the quality of the predictions that we provided, as well as provide any relevant experimental data for us to know. And in the back end, we implemented a small schema where we store user information and their uploaded MOF and their feedback entry and store into a database for future perusal. And the idea is that in the future, a grad student will hopefully be able to use this feedback to improve our machine learning models down the line. So for these two websites, the impact continues to grow. MulSimplify Lite in the past 3 years had 22K visitors with 55K requests total, and MulSimplify has had 10K visitors, and we've had 18 actual feedback entries from experimentalists, and these numbers will only continue to grow. I will quickly run through this part. So the last thing I want to show you guys is Ligandify, which is a website that we developed to predict the synthesizability of a transition metal complex. And the question is whether we can use machine learning to determine whether a complex will hold up in solution based on its component parts. So for this work, we're interested in tetrahedral complexes containing 2 ligands, one monodentate and one tridentate. So the monodentate ligand only attaches at 1 point, and the tridentate ligand attaches at 3 points. And the question we have is whether, if we're given a pair of ligands, whether they will form a synthesizable tetrahedral complex. So here I show an example of such a complex. On the left, we have a tridentate ligand attached to a nickel atom. We have a monodentate ligand, chloride, and this atom attaches to the nickel complex to form a tetrahedral complex. As you can see, the central nickel is surrounded by a tetrahedral cage of atoms. So what we did is that we scraped the Cambridge structural database for a set of unique ligands. We found 969 tridentate ligands in this space of 3+1 complexes. We found 634 monodentate ligands. And if you multiply these two numbers, you can assemble about 600K possible transition metal complexes. And the number of these that we found in the CSD is about 2,000. So about 99.64% of this chemical space hasn't been explored experimentally. So what we did is that we used stochastic negative addition, which is a technique where we randomly combine ligands together and assume them to be unsynthesizable, and use that as our negative data, and use examples from the Cambridge structural database as positive data to train a classifier to decide whether two ligands are pairable or not. And to see whether we can learn anything from this type of data set, I did a unsupervised classification of the two data sets, and we find that the synthetically generated complexes lie in one region of space, and the ones that are actually found in experimental databases lie in another region of space. So this shows that by randomly assigning ligands together, we can generate a data set of not synthesized compounds that are likely not synthesizable. So we developed a machine learning classifier to predict the synthesizability of these complexes based on their components. The accuracy of this classifier was 87%. On the right, you can see a curve that shows the true positive rate versus the false positive rate for various classifier thresholds. And we find that the optimal threshold, it has fairly good performance. So for Ligandify, this QR code links to the live website. And the interface allows users to find coligands for a provided ligand and uses a machine learning classifier in the backend, which I've described previously. So some features of the website are that it allows users to interactively explore the top 5 outputs of the classifier for different ligands that they input. So in frame A here, you have an empty cell. In frame B, they input a ligand. And in frame C, they get a list of the top 5 candidates that compare with this ligand. And because this website is interactive, a user can modify their ligands, make small perturbations, and see how the model's behavior changes, which helps them interpret the model. And they can also get a CSV download of ligand metadata that we computed. So the key takeaway here is that interactive tools can make our machine learning models more accessible and accelerate design. So to conclude the website portion of this talk, which will also conclude the talk after acknowledgements, is that websites as user interfaces for machine learning models can make our machine learning models more accessible to end users. And the impact of these websites continues to grow. As I mentioned earlier, Simplify has received 55K requests, Simplify has received 10K visitors, and these numbers will only grow over time. And for Ligandify, time will tell. And with that, I'd like to acknowledge my committee. I'd like to acknowledge my funding sources. And I'd like to acknowledge the Kulik group for tons of support, technical support, and this lively conversation, very interesting conversation about chemistry. I'd also like to thank the many group alumni who've helped me along the way. And of course, Professor Kulik herself for going very above and beyond, in my opinion, an advisor's duty to make sure I'm shepherded through this PhD process. So I'd also like to quickly go through some fun acknowledgements through friends and family. So of course, I'd like to thank the Arunachalams, that's my mom, my dad, and my sister. They've been a valuable source of support for me in making it to this current position. I'd also like to acknowledge some really cool crews. So in high school, I was really into calculator programming, like TI-84s. So shout out to Sean and Brian and Simon for that. I'd also like to acknowledge the Caltech community, especially my roommates, Wayne and Jonathan, undergrad, and also friends I made during the pandemic. Michelle and Aubrey, I probably chatted like endless hours with you guys. With the MIT and Greater Boston community, I'm not going to name names. It will take absolutely forever. But the people included under this umbrella include many quite random groups. Like the startup Blend Shift that I worked on, team there. A crew of us that get up at 9 a.m. for no reason. And then a bunch of Norwegians from NTNU for some reason. And again, I can't name specific names because there's just so much interesting, cool stuff happening in Boston. Pretty much all these photos were probably taken in the span of 3 months. It's just been a wild ride. And lastly, of course, I'd like to thank the cats of MIT. So in clockwise order, you have Murray, Pika, and Mika. Mika is currently staying in our dorm in SIDPAC illegally. Don't tell anyone. And lastly, I'd like to thank my mentors in the business and startup world. I'd like to thank MIT Sandbox for generous support when we're working on Lens Shift, the Martin Trust Center for helping with entrepreneurship resources and connections, and Global Founders Capital for introducing me to the world of venture capital consulting. We're going forward. I'll be taking a stab at my dream job of independent consulting in the space of VC. So I'm pretty excited for that. And that's all. Thanks.
Great. Naveen, obviously we can't see, but maybe you can see if there's any questions from in the room or from on Zoom. This would be now the time for folks to speak up.
Actually, it says clap. Thank you, Akshay.
So maybe one question, do you have any ideas how you would incorporate the human feedback into giving better, that improving your embedded models?
Yeah, so we do ask human users to provide a star rating from 1 to 5, which we could interpret as good or bad. The idea is that if there's something terribly wrong with our machine learning models, this feedback will alert us to it. So specifically, the machine learning models in that work were trained on data sets that were processed using natural language processing, and there's a lot of automation going on and reading the outputs of journal articles. So there's a possibility of like corrupted data and so on and so forth to correct. Yeah.
Is there any filter on the humans providing feedback?
What's that?
Is there any filter on humans providing feedback? So if somebody like doesn't have knowledge and provides that feedback, that would make the data support for feedback.
Yeah, so there is a notion of machine learning guided by expert feedback. One like popular science example of this would be reinforcement learning with human feedback, which is what GPT was trained on. To my knowledge, there's ways to incorporate this feedback, but the specific technical details vary based on the application. I saw another question back there. No? Yeah.
So, great presentation. I was just curious, what would are there any edge cases within your research of ligand structures in regards to, like, are they all in this design space? Would they all, in terms of the data set, are they all equally, like, equal? Is all data equal in the confines of your data set, or are there any edge cases? I'm not sure how you can construe structure as an edge case. Yeah, I do not know. I'm just curious. And the reason why is because then I'm asking about this because that's like a common problem with machine learning.
So one possible edge case that you might encounter is if you have very large ligands, they might interact with each other in unexpected ways. So you might find that this ligand, when it's trans to itself, might not have an issue, but when it's cis to itself, it's placed very close to another image of itself, which is very bulky, and these ligands can interact with each other. And this would not be predicted or anticipated by a machine learning model that's just operating based on the connections between atoms because it doesn't know about the 3D geometry. It'll just predict the trans to have a similar energy to the cis.
Were you able to, follow question?
Yeah.
Were you able to accommodate this, like within your, like, predictions, et cetera, machine learning?
So one potential way to accommodate it is to actually include some geometry data in our machine learning models. So you might recall that we convert our molecules to vectors, not using the 3D structure of the molecule, we just use a graph representation of it. But what we can do is do a very quick geometry optimization to get an approximate geometry of the structure. And then we can use that information to inform our vectorization. Any other questions?
Well, are there no more questions in the room? I don't see any questions on Zoom, so this would be the point where we would ask folks to leave and just Naveen stays. I don't think we need Adrian yet for the breakout room, but unless other folks are hanging on the Zoom. So I'm just waiting for the folks on Zoom to clear out, except for Klavs and Yuiry.
Probably better just to use the breakout point from,
Okay.
because then you don't have. So
Give me just 1 second and I will
Okay.
convene Heather, Klaus, and Yuiry. Just 1 moment.
I think so.
Naveen, I'm going to open room 1, but you are going to have to join it manually because you are the host of this Zoom, okay?
Sure.
Okay. Yuiry, do you wanna go first or?
Sure. Naveen, yeah, we're all very happy with the presentation that you gave. We thought it was done really, really nicely, and you were able to, yeah, put together kind of like the thread of all the different stories and all the different things that you worked. Very impressive work. A suggestion that we're discussing as the committee, as you remember from the plan to finish, a very important item that we discussed was this idea that we wanted to make sure that all the work that you put forward, we could put together in a manuscript, right? So I can share from my experience, and I think maybe Heather and Klavs will agree. Once you leave, everything becomes orders of magnitude slower in terms of doing that, because you will be busy with a whole bunch of other stuff, Naveen. And so we would like to strongly encourage you to see if you can find the time to package together what you have, to try to set up, not maybe like a final, super polished draft, but a draft of a manuscript with this work that you did. And make sure that you have enough time for the handshaking with everybody else, which I think you have done. But I think it would be very valuable while everything is fresh, while you are done already with the presentation, and before you leave. I don't know exactly when your last day is, but try to spend this time, Naveen, to package it, because once you leave, everything will become much harder to do. Not harder in terms of how difficult it is, but just finding the bandwidth and the time to put this together. But excellent work on the presentation.
Thank you.
So I guess with that, I will say virtually, congratulations, doctor. You can go ahead and go celebrate. So I think there's a mug and champagne waiting for you, and a party. And thanks Klaus and Yuiry for making it to this early morning defense.
No
Thank
problem.
you.
Congratulations, Naveen.
Thank you.
Congrats, Naveen. Very well done.
Thanks.
Okay.
Okay.
Uh,
See ya.